Okay, so this is the next in our series of videos on limits for Math 1560 Calculus 1 at U of L for fall 2017. This will be the first of two videos on limits involving infinity, and in this first one we're going to consider cases where the limit itself is infinite, meaning the y value is infinite. So before we begin, just a remark on some terminology. You will occasionally see some talk of functions being bounded versus unbounded. The classic example of a bounded function would be something like, say, the sine function, right? We know that the sine function just oscillates back and forth between -1 and +1. So the absolute value of the sine function is never bigger than 1. It goes between -1 and +1. So that's an example of a bounded function, right? Unbounded functions, there's a couple of ways that you could have an unbounded function. Well, sometimes you have an unbounded function because the graph just goes on forever. So things like y equals x squared, y equals e to the x, things like that, right? Where the y values go off to infinity, but of course they only go off to infinity as x also goes off to infinity, right? So we're kind of looking at what happens at the edges of the domain, but the other way that you can get an unbounded function is if you have a vertical asymptote, right? So we can consider situations where the function becomes unbounded for finite values of x. The natural log function is another example, right? If I graph 1 over x, I know that the graph looks like this, right? And it goes off to infinity as x approaches 0 from either side. Similarly, the natural log function also has a vertical asymptote at 0. It goes off like that, right? So these are both functions that near 0 are not bounded because the y values go off to infinity. And that's the sort of behavior that we're interested in this video. Okay. So here's the definition. What does it mean to say that a function has an infinite limit? So it means we've got a function, as usual, it's defined on some interval, maybe not at the particular point that we're interested in, but everywhere else in the interval is defined. And we say that the limit of the function as we approach this value c, we say that that limit is infinity, and we write the usual symbol for infinity. So we say that limit is infinity if we can make the y values, if we can make the value of f of x as large as we want by getting x close enough to this value c. So as we get closer and closer to c, so think of c as telling you where there is some sort of vertical asymptote. As we get closer to that vertical asymptote, the y values get larger and larger and larger, right? And of course you can consider large positive values but also large negative values, so we might talk about a limit being infinity, but we might also talk about a limit being minus infinity, and both definitions are done the same. And you can also talk about one-sided infinite limits, right? So if we were talking about for this function that we had on the previous slide, f of x equals 1 over x, if we were considering the limit as x approaches 0 from the right, well, we could say that that's infinity. And if we considered the limit as x approaches 0 from the left, that's going to be minus infinity, right? The overall limit as x approaches 0 doesn't exist because those two one-sided limits don't agree, but the two one-sided limits are both infinite. Okay, a couple more examples. So we can certainly see graphically why these examples are true. Okay, so we'll draw some axes. Okay, here's the graph for 1 over x squared. Goes off like that, and it goes off towards plus infinity as you get close to 0 from either side. Here's the graph for, so I've gone with the log of the absolute value of x because the log function we know is only defined when x is positive, but you can also throw in the negative values if you first take the absolute value, and then you get this piece of the graph as well. My graphing skills on a tablet still need some practice. but we get something that looks like that. So in either case, we have infinite limits for these guys. Now, how do you see that these ones have infinite limits? For the natural logarithm, well, there's a little bit of work to understand that one. And in fact, the only way that you really understand this is in terms of its inverse relationship with the exponential function. And so basically we could say here something like, well, since, and I'm going to borrow some notation from the next video. If you consider the limit as x goes to minus infinity of e to the x, if you consider what happens to the exponential function as you go way out on the x-axis, remember here's the graph of e to the x, and so if you head off in this direction, the graph of the exponential function gets closer and closer and closer and closer to 0, right? So this limit is 0. You can kind of turn things around. Remember that you kind of exchange x and y values when you move between the exponential function and the logarithm. You can conclude that the limit as x approaches 0 from the right of the natural log is minus infinity, just by kind of comparing the two graphs. How do you see the first limit? How do you see the limit as x goes to 0 of 1 over x squared is infinity? How do you see that you can make that as large as you possibly want? Well, I mean, you could choose. One way to think about it is choose any number n, right? So you choose an n, as big as you possibly can. You choose the biggest number you can think of. Well, if you choose that n, I could just take x to be, right, I just have to take a number. Take x to be 1 over the square root of n. And now again, I mean, we're kind of looking at the same thing from two different sides. Obviously, if I take this this number here, I'm going to get that 1 over x squared is equal to n. And if I take x values that are slightly smaller than that, well then 1 over x squared will be slightly bigger, and so by choosing some number between 0 and 1 over n, I get a value of 1 over x squared that's bigger than this n. So certainly I can make 1 over x squared as big as I want. And the other, I guess, concern you might have is, well, does that mean x is approaching 0? Well, again, if you think about it, when I'm dividing by root n, right, whatever n is, if n is a really, really big number, dividing by a really, really big number, that's going to give me something that's really small. Right, so this is a small number, this is a big number. We have this kind of reciprocal relationship between the two. We could get into precise details, but the precise definitions of these is not something we worry about in Math 1560. Now, a few notes about one-sided limits, right? If we're dealing with a function like this, if we were to graph this thing, and I'm not going to do the whole graph, but notice that this is 1 over x minus 1 times x plus 1. There's a couple of vertical asymptotes. There's a vertical asymptote at x equals 1. There's a vertical asymptote at x equals minus 1. Okay, and so we know that as we come in towards these vertical asymptotes, we know that the graph's going to go off to infinity. We're not going to get a plus infinity, minus infinity. We're not sure which one it is. What can you do? Well, here's yet another situation where our friend the sine diagram comes to the rescue. We can draw ourselves a number line. We can mark off our two asymptotes. And we can ask ourselves, okay, in each interval less than minus 1, between minus 1 and 1, and then bigger than 1, what sign does the function have? Is it positive or is it negative, right? Well, if x is bigger than 1, if I put in a x value that's bigger than 1, then of course x squared is going to be bigger than minus 1. So the denominator is positive. The numerator is always 1, so the whole thing is positive, right? Similarly, it's going to be the same result out here because, of course, if I square a negative, the negative goes away, so it's the same story for negative values smaller than minus 1. And in between, if I take an x value between minus 1 and 1, that square is going to give me something that's smaller than minus 1, and my function is negative, right? For example, if I plug in x equals 0, I get minus 1. I know that's a point on the graph. So now I can answer things like if somebody says, okay, what is the limit as x approaches 1 from the left of f of x? So I look at my function, I look at the factored version here, I say, okay, I know that I've got a vertical asymptote there because putting x equals 1 gives me a 0 in the denominator. So I know it's going to infinity or possibly minus infinity. Which is it? Well, I say, okay, I'm approaching 1 from the left, so here's 1, and I'm just to the left of 1, so that puts me here. And in that region, what sign do I see? I see a minus sign. So my limit must be minus infinity. And so now I know that the graph is going to go like that, right? And I can similarly work out the other limits, right? I could say, for example, the limit as x approaches, let's say, minus 1 from the right. Well, I look at my number line again, and I say, okay, approaching minus 1 from the right means I'm in this region over here again, where it's negative, so I get minus infinity, and so on. If I was approaching 1 from the right, or if I was approaching minus 1 from the left, we can see that we would have positive infinity for those limits. And so near the other asymptotes, we've got behavior that looks like that. Okay. The last comment we'll make here is that you can deal with, so the topic that's related to infinite limits is that of a vertical asymptote. So you have a vertical asymptote whenever you have an infinite limit for a finite x value. Okay, so we saw that in all of these situations here. Okay, so if the limit is infinity or minus infinity, or even if just a one-sided limit is either plus or minus infinity, in all of these cases we would say that we have a vertical asymptote, right? And at a vertical asymptote, that just means that as we come in towards this point, right, we're interested in this point. This is my a value here, so x is equal to a. I've got my vertical line, and as I come in towards that vertical line, the graph shoots off towards infinity, right? So you might have this sort of behavior like that. I'll leave you with one thing to think about. You've probably been told before that a graph of a function can't cross a vertical asymptote, and this is true. And sometimes you're just told, well, that's because a function isn't defined at a point where you have a vertical asymptote. But I could always assign some value. I could assign, f of a equals 0 or something like that. I can assign a value, right? But I still have to have a break in the graph. I can never have a vertical asymptote and come across. So I'll let you think about why that could be. I'll tell you the answer, but you still have to fill in the reasoning. The answer is that if you cross a vertical asymptote, you no longer have a function, and I'll let you think about why that is.